Hello, everybody. Once again, we're going to start our lecture. We're going to learn another derivative rule. Now, this is a very important rule because it really starts to bring things together. It's a very encompassing rule. It works in a lot of different cases. And because of that, it's very general. And honestly, it's very tricky. So let's just let's do our best to make sure that we can all utilize this rule. So I have hopefully reviewed the correct 7 rules that we've talked about previously. Of course, remember, we have the definition of the derivative, we have the sum difference, constant multiplication, power, exponential, product, quotient, and we've also talked about some trigonometric identities. We're going to introduce another rule, which is based on what is sometimes referred to as functional composition. So, if I write something like this, or something like this, that is a product, and that is a quotient. There's a special, something you've probably seen in college algebra. It has a circle. It's called functional composition, where you compose one function with the other, f of g of x. And that's what we want to talk about, is this. What is the derivative of the composition of functions? Okay. Now, instead of g, we're usually going to rewrite that as u. But the text kind of jumps back and forth, so I will point out you can instead write this f of u, where u is a function of x. And here's what we get for the chain rule. The derivative with respect to x of some function of u is the derivative of f, leaving u normal, and then we multiply outside the derivative of u with respect to x. The derivative of the outside function, df du, times the derivative of the inside function, du dx. Most importantly, we work our way outside to inside. We first take a derivative of the outside, then we multiply that by the derivative of the inside. And I have a couple examples prepared that I want to walk through, and then we'll also look at some ourselves. So here's a function. I'm trying to hide some information. F of x equals 3x plus 4. And then we take that and we cube it. These are going to help us define what are our actually, let me match the colors. We have our inside function and our outside function. Our outside function is something, which we call u, is being cubed. And then the inside function is what that something is. And in this case, that inside function u is 3x squared plus 4. So, like with most things, we set up our table, we have f, and then I like to call it u. Again, these are what we sometimes call dummy variables, coming from the word dumb, meaning they don't speak, they don't change things. You know, they can't act with any agency. We've just assigned these things to them. They don't speak for themselves. We've assigned them their own meaning. Okay? Now, what is the derivative of something cubed? Well, that's the power rule. We bring down the 3 and reduce it by 1. We get 3 times something squared. And what's the derivative of 3x squared plus 4? Well, this one is again a power rule. We get 6x. The important thing is the composition. So notice, df du is 3u squared, 3 something squared. And in purple, I wrote 3 parentheses squared. But instead of writing the letter u, I'm going to replace it with what I know u to be, which is 3x squared plus 4. That's what I found in red. And then, finally, we have to multiply it by du dx, which is this 6x term. Now, we can simplify by multiplying the 3 and the 6, and we get 18x times the quantity, 3x squared plus 4, quantity squared. This is the derivative of f. And this is as simplified as it can be. Okay, this is a challenging one, and it's one that appears on your homework, so I actually went ahead and did it for you, just because I wanted you to be able to see it. Okay, so we have f of x is the square root of x plus the square root of x. Now, first thing I'm always going to do, remember, I'll write that right here. Remember to rewrite your radicals as powers, which I'm going to rewrite as x plus x to the 1/2, all raised to the power 1/2. So outside, we have something raised to the power of 1/2. Inside is x plus x to the 1/2. So we have our outside u to the 1/2, which power rule, bring down the 1/2, reduce it by 1. We have the inside x plus x to the 1/2, same thing. And then notice we put it all together, where we have 1/2 times something, but over here, what is that something? It's x plus x to the 1/2. Now, I also want to point out, this what I circled in red, this is good enough to get the right answer. If you wanted to simplify it, you could get it to here. But I will point out, most of these type of simplifications are not required. Versus this simplification, the 3 times the 6, that is a required simplification. So I just want to denote the differences there. Okay, let's do one live. Let's do one that I haven't done before, and let's see if we can find it out. So we're going to find d over dx of 7x times cosine of 2x cubed. Okay, this is an interesting one because I want to point out that there's going to be multiple rules involving here. And we all, again, going back to our rule, we work our way outside to inside. So outside, I see this function and this function is a product rule. I'm going to multiply these two functions together, which means I need to use the product rule. So I'll call the first one f, and I'll call the second one g. Okay, so f is 7x. What does that make f prime? Well, 7. Whereas g is cosine of 2x cubed. And the question is, what is the cosine of 2x cubed? And this is a very common technique whenever you're using these tables, which is that you recognize that whatever this derivative is going to be, it's going to come from another rule. Specifically, I need a chain rule. So again, the process of finding derivatives is about breaking them down into smaller pieces. And as a guiding principle, I want to remind ourselves, we work our way outside to inside. The outermost thing that's happening between these two functions is multiplication. That's why I start with the product rule. Now, upon going inside, I discover a chain rule, which I'll deal with right here in blue. Now, again, I'm going to reuse the labels f and u, but again, these labels aren't all-consuming. So we're going to have cosine of u, cosine of something, and the derivative of that is going to be negative sine of something. Okay? Now, what is that something? It's going to be 2x cubed, and the derivative of that, again, power rule, is going to be 6x. So remember, putting it all together, it's df over du evaluated at u times du over dx, which is just to say we're going to plug in what we know u to be. So for this rule, I'm going to get negative sine of something. And what is that something? 2x cubed. Don't forget that I'm going to multiply times the du dx, which is going to give me negative 6x. Well, I'm sorry, it's a negative from the beginning. Okay, now don't forget, this started with a product rule. And now that I found the f and the g and the f prime and the g prime for the product rule, I'm ready to write the derivative. It's going to be f times g prime. Now, that's going to be 7x times negative 6x times the sine of 2x cubed plus g times f prime, which is going to be 7 times the cosine of 2x cubed. And there is a simplification I can make. I can multiply the 7 times the 6. and I can multiply the two 6's to get negative 42x squared sine of 2x cubed plus 7 times the cosine of 2x cubed. And I'll be honest, that's pretty much the best way I have to write this. Some people would tell you to switch these so we don't start with a negative sign. Again, I'm completely fine with the way that that looks. Okay, so this is how you utilize things like the chain rule. The important thing is that the chain rule is going to be our connection between a lot of different rules. Okay, and there's often going to be this whole branching idea where in order to fill out the table for a product rule or a quotient rule, we might need a chain rule or we might need a product rule to help finish the chain rule. Okay, let's do one that I just make up. I'm going to say, let's find the derivative with respect to x of 2x cubed e. You know what? Let's do a derivative. Let's do a quotient rule. Let's do 2x plus 1 divided by e to the negative 15x. Okay? So, once again, outside in, I get a quotient rule. Now, I like to call these p's and q's. For the numerator and the denominator, it's going to be 2x plus 1. It's going to be e to the negative 15x. So, what does that make p prime, and what does that make q prime? Well, p prime is 2, and q prime is going to be a chain rule. Because I have an outside function, e to the something, and I have an inside function, negative 15x. So, what's the derivative of e to the something? Still e to the something. What's the derivative of negative 15x? Negative 15. Reminder, we write this with this inside, and then we multiply by this. So what is that going to be? It's going to be e to the something, where that something is negative 15x, times negative 15. Now that I have this, I'm ready to write the quotient rule, which, reminder, is, in my language, qp prime minus q prime p all over q squared, using q's and p's. I think I used f and g's to write the rule above. So that's going to be e to the negative 15x times p prime minus q prime times p, all over q squared. Now, can I simplify this? The answer is yes. Point out this term has an e to the negative 15x and this term has an e to the negative 15x. Notice, subtracting the negative, they're going to turn these positive. I can rewrite this as e to the negative 15x times 2 plus 2x plus 1 all over e to the negative 15x squared. And one of these will cancel with one of these, leaving me with 2x plus 3 over e to the negative 15x. But I will point out, once again, this is an example where this, sorry I wrote through that, is good enough. The only simplifications you have to do is combining like powers through multiplication, and you also have to combine constants where appropriate. These are the required. Wow, I really butchered that. But I don't want to confuse you when you look at this as a reference. Okay, the chain rule is difficult. I expect that there may be some questions that you want me to do. If you have a question, send it to me, and I will include it in a video. So, tell me one of the ones that maybe you're having troubles with, and I'll certainly do whatever I can to help you. Have a wonderful rest of your day, and please, let me know if I can do anything for you. Take care.